Hello dear students, in this lecture we are going to learn more important aspects about ambipolar diffusion in plasma. In the last lecture we have derived the ambipolar diffusion coefficient for plasma, which looks something like this. Right. So, this is a function of temperature of electrons and ions, mass of ions and the collision frequency of ions. So, the basic understanding is despite the differences between electrons and ions in terms of mass, both velocities will be the same or both the particles will diffuse at the same rate. So, this kind of diffusion process is known as the ambipolar diffusion, and this is a very peculiar process specific only to plasma. So, if the electrons and ions have the same temperature, we can say that the ambipolar diffusion coefficient and the plasma scale height have twice the value in comparison to the neutral gas having the same molecules the size of ion, right. So, if you bring the diffusion coefficient, we know it is kBT by m nu, right. Now, what I was saying is, if the electron temperature is equal to the ion temperature, the ambipolar diffusion coefficient will be kB times 2 kB times T divided by mi nu I, which is actually twice the. So, the ambipolar diffusion coefficient is twice the diffusion coefficient for normal neutral gas, and if you consider the plasma scale height, which is Hp, the plasma scale height as kB times Te plus Ti by mg. For electron temperature equal to the ion temperature, you can write the plasma scale height to be twice the scale height of an identical gas which has the same molecules or atoms, but in the neutral state, right. So, one very important thing is the plasma, the ambipolar diffusion is peculiar to plasma. Okay. Now, you can write the flux of particles. So, flux which can be written as gamma as n times uj, number of particles per unit volume times the velocity. So, it is basically the fields that are set up when these electrons try to move faster are responsible for bringing the ions to larger velocities, or both of them traveling together, or both of them diffusing together. So, this diffusion is what is responsible for the solar wind travel from sun to the earth. What we will do in this class is we will try to understand more aspects of this ambipolar diffusion, or the same process explained in terms of different set of variables. Okay. So, solar wind, as we know, consists of electrons and ions, both of them travel at the same speed. If their masses are so much different, then obviously the question is why they should travel with the same velocity, and the answer is basically the ambipolar diffusion, which is a very specific process which happens only in the plasma. Okay. So, the effect of electron is to double the scale height. You see, the velocity will be doubling the scale height. To understand this even further, let us assume an equilibrium situation when the velocity w is equal to 0. Okay. So, let us say the temperatures are equal, Te is equal to Ti, let us say we call it as T, and we know that the mass of electron will be much smaller than the mass of ion. So, we can neglect something that appears to be the multiple of mass of electron. Right. So, we can write the simple equation as dP by dH minus mi g n plus E E n is equals to 0, or same equation as minus kT by n dN by dH minus mig plus EE is equals to 0, or minus kT by n dN by dH minus EE is equals to 0. So, this is for obviously for ion and this is for electron. So, I am not writing temperature Ti and Te because I assumed both of them to be the same, and in the electron equation I have not written the Meg term because the mass of electron being very small, we can neglect it. So, let us say we call this equation as equation A and this as B. So, adding both of them, what we will get is 1 by n dn by dh is equals to minus Mig by 2 kT, which is minus 1 by Hp, and this can be called as equation number C. Now, we can use this equation number C in B, in the electron equation, and we can write what is equation B, K minus kT by n dn by dh minus EE is equals to 0 minus kBT by n dn by dh minus EE is equals to 0. So, P is equals to n kT, n is the number of particles per unit volume, and if you E is the electric field, so we can write minus kBT times minus Mig, 1 by dn by dh is Mig by 2 kT, right, Mig by 2 kT is equal to EE, right. So, what I have done? I have 1 by n dn by dh, this is what I have substituted, right. So, I can write cancelling out things that are appearing both sides, we can write Mig by 2 is equals to E times E. What is E? E is the electric field, small e is the charge, Mi is the mass of ion, J is the gravitational pull, right. So, this force, how does it come into existence? EE. This comes into existence because the electrons being lighter, they move faster, they set up an electric field. This electric field will try to decelerate the electrons, but this electric field is building up a force against the electrons, which is given by EE, right. So, now we can see this equation and we can understand one very important aspect. So, the electric field E acts on the electron with a force which is equal to half Mig, right, isn't it? So, this is for the electrons, the equation that we have picked up is for the electrons. So, it appears the force on the right hand side is equal to, as if the force is half the mass of ion times the gravitational pull. So, it is natural, we can say that the electrons will behave as if they have a mass of Mi by 2. You see this? Because of the opposing electric field to the electrons will behave as if they have a mass of Mi by 2. So, this force is, what is the direction of this force? This force is downwards along the gravitational pull. So, same force will naturally act in the upward direction for the ions, right. So, this is dn by dh, you can use it in this equation and realize that this force will be exactly opposite to the ions. But the point is, due to the electric field, the electrons will behave as if they are moving with a mass of Mi by 2, half the mass of ions. Okay. Now, the magnitude of this electric field E is Mig by 2E, is very small, right. Now, if you take for instance the case of Earth's ionospheric plasma, which consists of oxygen ions, the oxygen ions Mi, I am referring to Mi, and E is the charge of electron. So, if you take for ionosphere of the Earth, where the majority positive charge carriers are oxygen ions, in that case if you put that mass to perspective, you will realize that the electric field that I am talking about is approximately of the order of 10 to the power of minus 6 units. So, this is the amount of electric field which is decelerating the electrons. So, correspondingly, if you want to find out what is the surface charge density, we can write the electric field as sigma by epsilon naught, or number of charge carriers per unit volume multiplied by the charge times delta x, right. So, we can use E as kT by Ne dN by dH. Now, delta x can be written as epsilon naught kBT divided by Ne square times 1 by N dN by dH. Yeah, so this goes here, right, and equating these two, I have written a relation for delta x. So, in terms of things that we know, delta x is epsilon naught kT by Ne square. This is a very familiar term that we know very well, which is nothing but lambda d square by some delta. Okay. So, where is lambda d square is nothing but the lambda d is nothing but the device length, and delta is just a distribution height. What is distribution height? This one, 1 by N dN by dH. So, you take N is equals to N naught exponential minus h by h, and then you take a derivative and do this, you will realize what is the distribution height, right. So, what have we learnt? We learnt that how the electric field acts on the electron and what is the effect of this electric field, how the electrons will move as if they have a mass of half the mass of ions, and typically what is the electric field magnitude. Okay. Now, we will try to define ambipolar diffusion by introducing the mobility. What is mobility? Mobility is drift per unit electric field basically, right. So, for any species, for charge species, the fluid equations of motion are very well known to us. We have discussed at very fine detail about this fluid equations at large lengths. So, dV by dt plus V dot del times V is equals to plus minus E N E minus del P minus M N eta V. So, this plus minus symbol is for accommodating both the charges. So, let us assume a steady state. What is steady state? In which velocity is not 0, velocity is actually a constant. It is not changing with respect to time. So, the forces are exactly balanced and velocity is a constant. So, in the steady state, it will be forcing on the collisions. Okay. So, we can make an assumption that the collision frequency to be very, very large. Okay. So, in that case, when the velocity is constant, we have the entire left hand side becoming 0, and we can write plus minus E N E minus del P minus M N eta V is equals to 0, or we can write that steady state velocity as 1 by M N nu times plus minus E N E minus K B T delta n. So, you can work out the algebra, it is pretty much simple actually, right. So, I have written pressure gradient in terms of density gradient using the ideal gas equation in between. Okay. So, the velocity can further be simplified or arranged plus minus E by m nu times E minus kBT by m nu times delta n. Of course, this is still ambipolar diffusion, but now we have brought in the idea of collisions. So, this can be treated as a velocity which the particles will achieve when there are many number of collisions, right. Now, in this expression, you see this E by m nu. What is this? This is called as the mobility, and you have kBt by m nu. What is this? This is called as the diffusion coefficient, right. So, we can write mu, the transport coefficients can be suitably adjusted, and we can write mu as q t by kBt. So, gotten rid of the collisional frequency in the mobility expression. So, the velocity v, the steady state velocity which is achieved as a result of collisions, constant collisions, is, this is some sort of a drift velocity actually, right, minus d times delta n by n. Okay. You can just look at these equations, write them down and build up the algebra that is there in between, okay, the intermediate algebra. Okay. So, this is the velocity in terms of the mobility. Okay. So, now when you consider a particular species, okay, the flux with which the species is diffusing, we write it as gamma j as n Vj, which is now going to be written as plus minus mu j n E minus the diffusion coefficient of the jth species multiplied by delta n. This is the flux of the jth species. Okay. Now, when we talk about flux, we need to remember a very famous law, which is a Fick's law of diffusion. We can slightly modify and make a special case when the electric field is 0, and we can get back the Fick's law as gamma is minus d times delta n. What is this? This is the Fick's law. All right. So, what you do is, what you see is the effect of ambipolar diffusion is to get a picture in which electrons are behaving as if they have a half the mass of ions, and at the same time the ions have a diffusion coefficient which is twice, or which should have been smaller by a factor of 2 ideally, right. So, the effect of ambipolar diffusion is to increase the mobility of the ions by a factor of 2. Okay. Now, we can get the flux in terms of the mobilities of electrons and ions separately. Let us see how we get it. Okay. So, we will write gamma from the earlier relation using this mobility mu n e plus minus mu n e minus dj del n. So, for ions it will be plus mu n e minus d delta n, and for ions it will be exactly minus in the first term. So, gamma is mu I n e minus d I delta n, which is mu e n e minus d e delta n. So, from these two equations, the electric field E can be written as d I minus d e divided by mu I plus mu e times delta n by n. We can use this electric field in any of the flux of ions or electrons to write gamma I as mu I times n times d I minus d e divided by mu I plus mu e delta n by n minus d I delta n. So, slightly arranging the terms, gamma I is mu I d I minus mu I d e mu is gamma is minus mu I dE plus mu E dI, cancelling out all the terms, mu I plus mu E times delta n. What is this? This is the flux, right. Now, this is again the Fick's law. We've gotten back to the Fick's law, nothing else, but the diffusion coefficient is slightly modified now. The entire thing, that is, this is the diffusion coefficient. This is the ambipolar diffusion coefficient, which is mu I dE plus mu E dI divided by mu I plus mu E. This is the diffusion coefficient, right. Now, let us see some features of this diffusion coefficient. What is this called as? This is called as the ambipolar diffusion coefficient. Now, we know that the mobility is proportional to 1 by mass. Larger the particle, smaller will be its mobility, right. So, the mobility of electron will obviously be much larger than the mobility of ion, and it is natural for us to expect mu E plus mu I should just be equal to mu E, because the mobility of ion will be very, very small. If you put this into this expression, the ambipolar diffusion coefficient, which we have written in many forms so far, is mu I divided by mu E times dE plus dI. You see this? I just substituted mu I plus mu E as just mu E, that is it. Okay. So, once we have only mu E in the denominator, in the numerator we are not changing anything, mu E will get cancelled in the second term, and as a result only dI will remain, right. So, the ambipolar diffusion coefficient is now a ratio of the mobilities multiplied by the diffusion coefficient of electron plus the diffusion coefficient of ions, right. Now, where do we go ahead of this from this? Okay. So, mobility from basic definition is q times d divided by kBt, right. So, for the remaining things to be constants, so the diffusion coefficient by temperature is a constant. So, dE Ti divided by dI Te will be a constant, and this constant is going to be mu E by mu I, right. So, from this we can get this ratio of mu I by mu E dE, rearranging the terms will be Te divided by Ti times dI. So, we can bring this here and write the ambipolar diffusion coefficient is nothing but Te divided by Ti times dI plus dE. So, we have dI. So, by doing this, we have not just eliminated the ratio of mobility, we written the ratio of mobilities in terms of the temperatures, and also eliminated one diffusion coefficient. Now, the earlier version of the ambipolar diffusion coefficient has two electron and ion diffusion coefficient. Now, we have only ion, right. Now, in a situation when the electron temperature is equal to the ion temperature, the ambipolar diffusion coefficient dA simply becomes dI plus dI, see, or dA is twice the diffusion coefficient of ion. So, now we can summarize all these things. So, the effect of ambipolar electric field is to increase the diffusion of ions by a factor of 2 and make electrons move as if they have a mass of Mi by 2. So, these two factors are important. Mi by 2 is going to be the mass of electron, and the diffusion coefficient of is twice the diffusion coefficient of ion. So, the effect of ambipolar diffusion or ambipolar electric field is to increase the diffusion of ions by a factor of 2. That is how they will start moving with the same velocity. Right. Now, let us consider the diffusion of weakly ionized plasma in the presence of a magnetic field. Okay. So far we have considered the general nature of ambipolar diffusion. Having understood all these things, let us consider the diffusion of weakly ionized plasma in the presence of a magnetic field. So, diffusion parallel to the magnetic field will not be influenced by the magnetic field, right. So, we will only consider direction which is perpendicular to that. So, we will start with our basic equation Mn d u perpendicular by dt is q n e plus u perpendicular cross b minus k b t del n minus mn nu u perpendicular, right. So, this has to be a total derivative. So, the partial derivative will become 0 considering a steady state. So, what we will be left with is the advection term. So, since these things are very much familiar to you or we have discussed multiple number of times. So, what we are interested is to find out an expression for u perpendicular. So, u perpendicular, so this has to be expanded to total derivative, and steady state means dou u perpendicular by dou t becoming 0. So, solving for u perpendicular, we can get u perpendicular as mu perpendicular times E minus d perpendicular delta n by n plus omega c square times ue plus ud by omega c square nu square. So, this ue is nothing but the E cross B drift velocity, ud is the diamagnetic drift velocity, ue is E cross B by B square, and ud is minus del P cross B by B square. So, we can, with the help of this, by just doing some simple algebra, we can define the perpendicular mobility mu perpendicular as q by mv divided by 1 plus omega c square tau square, and the perpendicular diffusion coefficient as kbt by mu divided by 1 plus omega c square tau square. So, what we can see is that the perpendicular motion of particle contains two parts. One, the usual drift which are impeded by collisions, and mobility and diffusion drifts along the gradient in the potential and number densities, right. So, with this we conclude the ambipolar diffusion. In the subsequent lectures, we will try to understand various applications of plasma physics, or how plasma can be used as a tool in material science or in photonics or many other things.